So here we go. Yeah, all right. So today we are going to be finishing up our notes on the following objects that we started on Tuesday. My plan on Tuesday was that we would have finished the notes on Tuesday, and then today we would be going through how to build a launcher. And then next week we were going to be doing this cool lab using our catapults and launchers that that I would be building for you. But I learned yesterday during my meeting that we have decided to stop classes 1 week early. So for those of you just joining us, I was telling you that 1 week from tomorrow, May 22nd, that's a big day. It is your last day of classes. I should say, actually, your last day of classes will be that Thursday, May 21st. And then that Friday, May 22nd is considered kind of the last day, I guess the last day of school. For most of you, you'll be done at that point. There is a test on that day, which is May 22nd. You're going to have a history test. You're also going to have a science test. Your last test of the year for science and for history. And I think, period, I think that's it for you guys this year. Now, this test is going to be on Socrative, and it's going to be open from 11 a.m. to 3 p.m. on that Friday, May 22nd. So it'll be multiple choice. Just sign in to Socrative. I'll give you a room number that I'll post on Edsby, and you can just take the test at your leisure, and you can use your notes. So the notes on Newton's laws that I gave everybody a copy of, plus you all took those notes, you want to have those with you on the test. You also can have these notes with you on the test that we're finishing today. And the last things for a grade, other than the test on Friday of a week from Friday, is 2 things that are due this Friday, as in tomorrow. And those are these notes that we're going to finish today, and Newton's, Angry Birds according to Newton. So your homework dealing with Angry Birds, and wanted to remind you guys of that. So I posed it. So you can get Angry Birds on your tablet or on your computer or your phone, and you can play any version of Angry Birds, and it's free. And you are writing strategies on how to, ooh, it's really windy, to win at this game, or to score high at this game using all 4 of Newton's laws. That would be law number 1, the law of inertia. All objects at rest will stay at rest. Objects in motion will stay in motion unless acted upon by an unbalanced force. Law 2, which is law of acceleration, says that force equals mass times acceleration. So the larger the mass, the more force you need to make it accelerate. And it's also related to momentum. So the more a larger object is going to be harder to make accelerate, but once it is accelerating, it's going to have a lot of force or momentum, so it'll be harder to stop. Third law says that for every action force, there is an equal and opposite reaction force. So when an Angry Bird is pushing, say, on a wall of the fort, of the piggy's fort, then the wall is pushing back equally on the bird. Now, if the bird bounces back off the wall, then it's because the bird has less mass than the wall. Or if the wall topples over, then it is not because the forces are unequal, it's because the mass of the wall was less than the bird's force of momentum. So anyway, equal and opposite reactions have to do with forces. So equal in strength of the force and opposite in direction. Remember, those forces aren't acting on the same object. So that is why the object may change its position. Okay, so you also have a fourth law, and the fourth law has to do with gravity, and that's what we've been talking about in these notes. So that is Newton's law of universal gravitation. All right, so going back to our slide to remind you of what we are doing. The Angry Birds is due tomorrow also. We talked about those 4 laws, so you're writing a strategy for succeeding on Angry Birds video game, using Newton's 4 laws plus projectile motion. And the projectile motion is the part we didn't get to on Tuesday, so that is the part we're going to focus on today. So if you've already done your Angry Birds, you might want to go back and look at this part of the projectile motion. And don't forget, there is a rubric posted for how I'm going to grade it, so what you need to include in your Angry Birds homework. There is a rubric for it, and there is a separate set of directions as well that has some review. Remember, you get to use your notes on the test, so any of those things, assignments and labs, might also be helpful to use on your test on Friday, May 22nd. Okay, so for today, all you actually need to have in front of you is your note worksheet, your notes on falling objects. And that looks like this right here. And we did about half of it on Tuesday. So on Tuesday, we did this whole first page, and yeah, pretty much the first page. And so today we are going to do the second page of the notes, which is just a little bit more about gravity and then getting into the projectile motion notes. So that is what we're doing right now. So hopefully you have those with you and we can get started. Okay. All right. So before we do get started, I set up a little game here of Angry Birds right now, and I was wondering if you guys could tell me. All right, let me get this so you guys can see the game and me. Okay, so I have a little pig fort set up right here, and I have also a big Angry Bird, and a smaller Angry Bird. Now, if I put this little bird in, and I shoot, or I fire my catapult at the fort. Oh no, it fell already. Okay, well, anyway, it went really far. Okay, I don't know if you could see that it went clear across my yard. Okay, now, if I put that same amount of force on this bird that has more mass, according to Newton's second law, what is its acceleration going to be compared to the smaller bird if I have the same amount of force but less mass? And let me remind you of Newton's second law right here. Force equals mass times acceleration. So if we increase the m, the mass of this bird, what will also increase? If I use the same force, so if I keep force the same, but I increase the m, what would Newton's second law say is probably going to happen to the a, the acceleration? You want? No one wants to answer that. Okay, so the it should accelerate less if given the same amount of force because it has more mass. So remember, according to Newton's second law, an object with more mass is going to require more force to make it accelerate. Or if it's given equal force as a smaller object, it's going to accelerate less because of that whole relationship between force, mass, and acceleration. And we're going to be looking at that law and rearranging Newton's second law to solve for acceleration when we're looking today at why a projectile, something that is dropped, will accelerate at the same rate, even though the force of gravity is different for them. And this only works in the absence of air. So if you can get rid of all the air resistance, the frictional drag on an object, all objects will accelerate with the same amount or at the same rate at 9.8 meters per second squared, almost 10 meters per second squared if you round it. Okay, so so in your Angry Birds homework, don't forget to think about things like that, like the second law. Like if you want your bird to travel to the pig sport with the same, going the same acceleration, but you have a larger bird, you're going to need to apply more force to make it go that same distance because it's got more mass. Okay, all right, so hopefully you're understanding that, and we're going back to our notes, and we are going to, let's see, somebody wanted to say something. Yeah, Derek, okay. All right, so notes, yes, notes. Okay, so we have our note worksheet out, and we're gonna look at this here. I'm going to, I think I'm gonna do this in slideshow mode. Yeah, okay. All right, so Tuesday, we started these notes and we were learning about universal gravitation, which is Newton's fourth law, terminal velocity, and projectile motion was something we didn't quite get to. So that's what we're going to look at today. All right, so I did want to do a quick review and would love for you guys to share, please, in the answers to my questions. So does anybody remember if gravity is a universal force? Do all objects that have mass experience some force of gravity? What do you think? John?
Yes, they do.
Yes, they do. But do they all experience the same amount of gravity?
No, because it depends on how much mass they have.
That's right. It depends on their amount of mass. So if an object has more mass, it's going to be attracted to another object with a greater force than if it were smaller. So the larger the objects are in mass, the more gravity between them. Now, the further the objects are apart from one another, the less amount of gravitational force between them. And although this isn't the same force as magnetism, I did want to compare it to magnetism for just a minute because you might be a little more familiar with playing around with magnets. And if you had a bigger magnet, two big magnets, and you put them really close to one another, they would want to come together. You would be able to feel that force. And if you happen to have a couple of magnets, maybe you don't have them handy because I just kind of thought of this, but you could actually feel the force. Now, if you had smaller magnets, you wouldn't feel the force as much if they were the same distance apart. And then if you took those same magnets, maybe the larger ones, but you had them further apart from one another, you wouldn't feel that force trying to pull it together as much as when they're closer. So think about that kind of like think about gravity kind of like magnetism in that respect, that it's dependent upon the size of the objects and how close they are together. All right, so that kind of helps us to set up for some of the rest of this. So we learned that in this example here, a house in Florida at sea level would have more gravity or more force of gravity pulling it to the earth than a house sitting on top of Mount Everest, because the house sitting on top of Mount Everest is further away from the earth than if they were on sea level here in Florida. Okay, and so yesterday our big mystery and our big question of the day, I guess, was, and again I said yesterday, I mean Tuesday. Tuesday our big question was, if we were to drop an elephant and a feather off of a tall building, would one of them fall faster than the other? Would one hit the ground quicker than the other? And you had to make a prediction of that. And I think that most people predicted that the elephant would fall faster and hit the ground first. And we learned that that actually is true. That would happen if we were to literally take an elephant and a feather and drop it off of a tall building. The elephant would hit the ground first because it has more mass and because it would be speeding up more than the feather. However, air resistance acts upon both of those. And so the reason that the elephant falls faster is actually not because it has more mass, it's because the feather reaches terminal velocity sooner than the elephant. And so we learned about what that means, and it's related to Newton's laws. So we know that gravity isn't the same for all objects, but we do know that the force, which could be gravity, because gravity is a force, is related to mass times acceleration. And if you were to have an object that was acted upon by an unbalanced force, it's going to accelerate. And it's going to keep on accelerating as long as the unbalanced force is acting upon it. So when an object is falling, it's accelerating due to gravity. But in the real world, if an object's falling and there is air, it's colliding with air. Somebody is not muted.
Is it in that drawer where
Sorry,
you
somebody
just found the
did.
system?
Could everybody mute themselves? I thought you guys were muted, but.
Thought I saw a thing like that.
Karen, your mic is on.
All right. Sorry, guys.
You're welcome.
Just stop everything to mute. Okay. I think. There we go. There was the issue. All right. So going back to our slide. Okay. All right. So anyway, we did learn that if an object is falling, it's being acted upon by gravity, and gravity is the unbalanced force making it accelerate. But we also learned that unless this object is falling in a vacuum where there is no air, it is colliding with air particles. And that is making like this frictional force that acts in opposition to gravity. So it's trying to slow the object down, whereas gravity is trying to pull it down. Air resistance is trying to push back in the opposite direction, which would be up in this case. Okay, so this one here. So we learned about air resistance and then how this relates to terminal velocity. So remember that according to Newton's second law, an object is going to continue to accelerate if an unbalanced force is acting on it. But according to Newton's third law, if forces acting on an object are, well, actually, let me rephrase that. According to Newton's first law, if all of all forces acting on an object are balanced, then the object continues to do whatever it's doing, right? If it's at rest, it stays at rest. If it's in motion, it stays in motion, if the forces are balanced, right? So what's happening here is when an object's falling, gravity is pulling it down and making it speed up, accelerate, because it's an unbalanced force. But as it's falling, air resistance, which is working in the opposite direction, is also increasing because it's colliding with more and more particles. And eventually, if an object can fall for long enough, depending on the mass of that object and the shape of the object, you know, so like the surface area of an object, like a feather, for example, has a lot of surface area. So air resistance is going to act on it. The faster it goes, the more air resistance. And eventually, if the object falls long enough, those two forces of air resistance and gravity will become balanced. And if they're balanced, what does Newton's first law say about an object in motion if the forces on it are balanced? The forces acting on an object are balanced and the object is in motion. What's it going to do? Newton's first law. All right, John?
Stay in motion?
It's going to stay in motion. And not just any old motion, but at a constant speed and in that same direction. So you see this, does anybody know what you call these diagrams right here? You had to draw them on Tuesday. They're called force diagrams. And the arrow represents, the size of the arrow represents the size of the force. And the direction of the arrow represents the direction of the force. So you can see in this picture here on the left and the force diagram on the left, before the parachute is deployed, you have the weight of this guy. Remember, weight is the force of gravity acting on the mass. So this is gravity. It is the person's weight. Is it the same for every person? No, because it depends on mass. So that's why we're calling this weight. It is that mass of that person times the force of gravity. And that's what's making that person fall. Air resistance is also acting on the person in the opposite direction. Right now you can see the arrows are not the same size, so the forces are not balanced. So what is this person doing right now? As far as their speed is concerned or their motion is concerned. Are they at rest? Are they moving? Are they speeding up, slowing down, constant speed? What's happening? You know what? Okay, well, then I will tell you that he's speeding up. He's accelerating because the force is unbalanced going downward. So he's falling downward and gaining speed. In the other picture here to the right, the force diagram a couple seconds later, now the parachute has deployed. Notice that now the force of air resistance is equal to the force of the weight, gravity pulling down on his mass. So they're both 500 newtons. You can see that the arrows are the same size, but different direction. Now what's he doing? Anyone? Yes, John?
Wouldn't he be going up, or would he be staying still?
So he'd be going up only if the force of air resistance going up was greater than the force going down. Then he would be going up. And I will tell you from experience that when I was skydiving, when I first deployed my parachute, I did actually go up because the force was greater at first. And I'm not exactly sure why. I think well, actually I do know why, because there's an additional force of the parachute coming up and out. So that added some force to it. So I initially went up, but once they're balanced, in this force diagram, it's showing that they're balanced. So that person now has reached terminal, well, technically that's not terminal velocity, but looking at it in a force diagram, it would be terminal velocity. He can't fall any faster than this, and he's now falling at a constant speed because the force of air resistance is equal to the force of gravity in the opposite direction. So the forces acting on the person are balanced, and therefore he doesn't accelerate. Okay, so that is what I hoped, well, getting back actually to the feather and the elephant thing, and putting all of that together with terminal velocity. The feather would hit terminal velocity first because it has less mass, so it has less force of gravity trying to balance it out. So what that'll mean, oh, we got somebody waiting to come in. So what that's going to mean is that the feather won't have to fall for as long before it actually reaches terminal velocity, because its force of gravity that it has to balance out is much less than the elephant, and air resistance is acting on it. It's got quite a bit of surface area. So the feather is going to stop accelerating quicker, and the elephant's going to keep on accelerating, because it would take a long distance for the elephant to hit terminal velocity. And I wanted to show you a video of the world's longest free fall, and it's in the Guinness Book of World Records. So I'm going to show you that here in just a second. I'm going to finish up this topic right here about what would happen if there was no air. So with air, the elephant's going to hit the ground first. But if there was some way we could take air out of the equation and really make for an actual projectile where the only thing acting on it is gravity and no air resistance, then believe it or not, and this is something that it's hard to understand, but they would actually hit the ground at the same time. And I showed you a video of a bowling ball and a feather being dropped in a vacuum, no air, hitting the ground at the same time. Tuesday. And the reason why is because the proportion between force of gravity in this case and the mass of the objects is proportional. So remember that a larger forced object is a larger massed object has a greater force acting on it to make it move, but it would also require a larger force to stop it from moving. So the proportion force divided by mass is equal. You have a bigger force and a bigger mass, that would be equal to a smaller force and a smaller mass. And that's how we end up with a number of 10, or technically 9.8, where is it? There it is, 9.8 meters per second squared. All objects accelerate. In the absence of air, all objects accelerate towards Earth at 9.8 meters per second squared. They don't all have the same force of gravity, but they all accelerate at the same rate if there is no air. And we know there is air, so that kind of throws things off a little bit. So let me share with you a video real quick of Felix Ambarger, jumping from 130,000 feet, which is the longest free fall.
If you're scared, walk away, 'cause there's no need to feel ashamed. Yeah, we all feel the same. Whoa, where's your passion? Where's your fire today?
Alright, now, the whole road is looking now. I'm going home now. Jumper away. Speed 725.
All right, so, and one other thing that I wanted to show you. Sorry, guys, it does not like it yet. Come on. There it is. Okay, it gets rid of my controls. Sorry, guys, on my video, and I can't see anything when it does that. All right, so the next thing I'm going to show you. Oh, no. All right. All right. So there's one in the background that may start playing. I hope it doesn't. All right. So I want you guys to also check out this footage. It is actual footage of David Scott, an astronaut in the Apollo 15 mission, dropping a hammer and a feather from on the moon, where there's very little air. Well, practically there isn't really any air. So this is as close as you can get to a vacuum, unless you actually go to that vacuum place at NASA that I showed you on Tuesday. Okay, so check this out. This is 19.
Well, in my left hand, I have a feather. In my right hand, a hammer. And I guess one of the reasons we got here today was because of a gentleman named Galileo a long time ago who made a rather significant discovery about falling objects in gravity fields. And we thought that where would be a better place to confirm his findings than on the moon. And so we thought we'd try it here for you. The feather happens to be appropriately a falcon feather for our falcon. And I'll drop the two of them here, and hopefully they'll hit the ground at the same time. How about that? It proves that Mr. Galileo was correct in his findings.
Okay. All right. So there we go. If I didn't put it in full screen, then you are able to, I was able to stop it better. Okay, so going back to our notes, now we're looking at some new stuff. And yeah, okay. So let's move on to this projectile motion part. Okay, so motion of a projectile. This is our new material. And how is everybody doing right now? Does anybody have any questions so far? No, nothing? Okay. All right. Well, here we go. So what is a projectile? Is going to be our first question here. Now, we're kind of learning that a true projectile is rare to find in everyday life. If truly a projectile is the only force acting on it is gravity. Because there is air resistance, you know, it's kind of hard to get away from that. But we're going to consider a projectile to be an object that is falling, and air resistance is there, but considered to be negligible, like not a major factor. Okay, so this object would be said to be in free fall. And there are different types of projectiles. So when projectiles move, we call these projectile motion. And when an object is being pulled down and only gravity is acting on it, we say that it's in free fall, which is what Felix Baumgarten was doing there when he was jumping out of the plane there. He was in free fall, and he reached a terminal velocity once the parachute's air resistance balanced out his force of gravity. So what you're going to do next is you're going to draw these pictures of the 3 different types of projectiles. So depending on your level of artistry, you can draw little stick people. Honestly, you don't even necessarily have to draw the person, but just show these 3 types of projectiles. One where a projectile is just going straight down, so an object is just being dropped. The second type is if you were to throw an object straight up into the air and then it came back down. And then the third object is throwing an object into the air, but at an angle. So you're throwing it at a horizontally at an angle and vertically up. So you then see a little bit more of an arc happening. And that is called a parabola. And we'll be looking at that today. I think while you're drawing this, I'm going to take a minute to explain something that I forgot to explain in the beginning. I started to tell you that my original plan was that we were going to be building launchers today, and then on Tuesday we would be doing a lab, and this lab had everything to do with projectile motion. And in the Physics Olympics, one of the events was an Angry Birds game that you would use your launcher for. And the Physics Olympics was an optional thing to do anyway. Well, since I learned yesterday that we are now done with school next Friday, a week from tomorrow, I'm not going to build the launcher. We're not going to do that lab, and we're not doing the Physics Olympics. So I had to cancel all of those things. So really what you are learning today, you will apply a little bit on your test on Friday, which is a week from tomorrow, not tomorrow. But you won't be using it on a lab and in our Olympics, unfortunately. So, but still gather the information. Remember, those of you that joined us a little late, the test is a week from tomorrow, and you can use your notes on it. So take good notes so that you can use them on the test. All right, and okay, so next is free body diagrams. Oh, that's right, you didn't draw free body diagrams on Tuesday. We hadn't gotten to it yet. So no wonder you didn't know the answer to the question I asked you a little earlier about what that picture is called. So these pictures are called free body diagrams. And what they are is just a little sketch, and they're not usually as fancy as the parachutes. They can be as simple as just a square or another shape and arrows acting on it. So you've got your object, and then the arrows on it represent the forces. The size of the arrow represents the size of the force, and the direction of the arrow points to the direction of the applied force. So in this free body diagram here on the left, by the way, you're drawing one of these, you don't have to draw both. This picture here on the left, the free body diagram on the left, shows an object that has all forces are balanced. You might notice that the force going up and the force going down are equal in size, opposite in direction. So those are balanced. You might wonder what a normal force is. Okay, so the force of gravity, which is an object's weight, right, is always going down. The force that acts in opposition to gravity when an object is at rest. Like, think about the pennies from heaven. When the stack of pennies was sitting on top of the card, remember they were on balanced forces. The pennies were pushing down on the card with their weight, gravity, and the card was pushing back up on the pennies. Well, that card pushing back up on the pennies is called the normal force. Okay, my computer right now is sitting on this table. The computer's putting a force on the table. The table is pushing back up on my computer with an equal amount of force, and that would be called the normal force. The forces acting in the left and right direction here are, if the object was trying to be pushed, there would be friction, because friction is a force that opposes motion when two objects are colliding or in connection with one another, when they are like sliding past one another. And applied force might be a push or a pull. Okay, so that's what all those things are showing. They show all the forces acting on an object. Can you tell me, could somebody tell me if this object here on the left in the free body diagram on the left, is this object moving? Or let me change my question. Is this object changing its motion? If it was in motion, would it be speeding up or slowing down? And if it was at rest, would it be, well, I guess speeding up or slowing down or changing directions? Anybody? What do you think? Oh, come on, guys. There's not many of you with me anymore. Okay, well, so this object would not be changing its motion because all the forces acting on it are balanced. So according to Newton's first law, an object with balanced forces acting on it will not change its motion. It will stay at rest or it will stay in motion. All right, so moving on now, we've got some more pictures to draw. So draw this picture of a cannon and, rudimentary drawn cannon on a rudimentary drawn cliff here, shooting a cannonball out going straight. So imagine if there was no gravity. If you were doing this, somewhere in space where you were far, far away from all other objects so that there was very little, if any, gravity, then the object would just keep on going in a straight line, right? Inertia. Keep on going until an unbalanced force changes it. So that is what would happen if there was no gravity. So we're kind of putting this projectile motion thing together. So remember that an object accelerates downward due to gravity at a constant rate. Not a constant speed, but a constant acceleration. So it means that it's speeding up at constant intervals. So that's if gravity is the only force acting on it, then it's going to speed up at regular intervals. Okay, and so now we're going to draw this. So now take the cannon that we shot the cannonball out of that would keep on going straight, but because now there's gravity, gravity is going to pull it down. So notice that this middle line right here is actually what we consider projectile motion. It's considered a parabola. And when we think of projectiles that are under the influence of gravity and some type of horizontal component, like it being fired out of the cannon, not just simply dropped, then it follows this arc right here. Notice this arc is kind of made up of the horizontal component, which is due to inertia, and the vertical component, which is due to gravity. And that's some fill-in-the-blank parts of what we just talked about. So the vertical component, why an object, like say the bird in Angry Birds, why is he eventually being pulled down to the ground? Gravity. Now, the horizontal component, in Angry Birds, when you shoot a bird out of the slingshot, you have applied a force. But once it is out of the slingshot and not touching the slingshot anymore, you are no longer applying a force to it. And it's going to just continue moving in that direction at that same speed until gravity pulls it down. Now, in the real world, there'd be some air resistance slowing it down, but in Angry Birds, they don't use air resistance. So it would be like in Newton's true first law, if no unbalanced force is acting on it, if there's no air resistance, it's going to continue at a constant velocity. All right. Now, Newton's law of inertia is what does that. Okay. This is a really common misconception that horizontal forces are required to make an object move. Horizontal forces are not required to keep an object moving horizontally. If the object is at rest, you do need to apply a force to make it move. But once that object is moving, it doesn't need a force to keep moving. Remember, that's inertia. Now, air resistance or other types of friction may cause it to slow down and eventually stop, but that's the unbalanced force acting on it. You don't need a force to keep an object moving, and that is really something that is misunderstood by a lot of people. All right, so remember that an object where the only force acting on it is gravity is said to be in free fall. So an object in free fall is being acted upon only by gravity. Air resistance would be negligible. And if that's the case, then the acceleration of that object is constant at 9.8 meters per second. Oops, that should say squared. Okay, because it's an acceleration, not a speed. It's accelerating or speeding up. And you can see in this diagram here that at every second, it speeds up the same amount. So it like doubles, then quadruples. And then so it's a constant acceleration. It's not speeding up more in 1 second and less in another second. It's speeding up the same amount each second. Okay, so going back to this picture again, I think this is the one where you're drawing the 3 components, or I'm sorry, these 3 paths. So looking at my notes here too to make sure I get you filling everything in. Okay, so I think that's where we're at right now. Draw that. Okay. Yep. You are drawing this right now. So this is the one that says, draw a picture of a cannon on a cliff, shooting a cannonball straight ahead, which it is right here. Show the 3 scenarios. One where there's no gravity. That's this first one right here. It got cut off, but it should say gravity-free path. The second one is where there is only gravity acting on it, falling straight down. And the third one where you've got the horizontal and the vertical components. Okay, and then it says to label them all. So go ahead and label them like I have labeled them. This says gravity free, or you could say no gravity here for this top one. Projectile motion for the middle one, and then vertical only, or gravity only. Well, no, vertical only would be better. Okay. All right. Moving on. Okay, this next one, you're showing the cannonball shooting up, instead of straight ahead, shooting up at an angle, which is how you would be playing Angry Birds. If there was no gravity, it would just keep on going at that straight path, you know, up at an angle there forever. But because there is gravity, it curves down, parabolic trajectory. And you're drawing that. We have one more little part to this, and I am almost out of time. The rest of this is math related, which now that we're not doing the lab, you are not gonna have, don't worry too much about this math, okay? Here's what I want you to know. Okay, if a cannonball is shot out of a cannon at a certain speed, say 20 meters per second, it's going to stay at 20 meters per second horizontally throughout its whole motion. Okay, according to Newton's first law, it's going to keep on going at that same constant speed in the same direction. Okay, if there wasn't friction, you know, acting on it, which we know in real life there would be. So understand that the horizontal motion will stay the same same speed because of inertia, and the vertical part will increase because gravity is the unbalanced force acting on it, and so it's not going to stay the same speed, it's going to accelerate, but it's going to accelerate at a constant rate. So when an object is in projectile motion, the horizontal component stays the same, and the vertical component going down is speeding up at a constant rate. And that particular number is 9.8 meters per second every second. So these three equations that I'm going to give you, I'll have you write them down to fill in these notes. And remember, you can use them on the test. So I may put one or two questions like this, but you just have your calculator and have these notes, and you'll have what you need. Okay, so an object that is being dropped. If you want to find out how far an object falls, like how far this apple fell out of the tree to hit Newton in the head, you would do this equation: half, or 0.5 times g, which is 9.8, always 9.8. So 0.5 times 9.8 times the amount of time it's falling. So this t would be given to you. If the apple fell for 4 seconds, then you would do 0.5 times 9.8 times 4 squared, which would be 4 times 4, which is 16. And then you would be able to find out how far the apple traveled. Y then, in this case, is the distance traveled vertically. Think about the y-axis on a graph. That's why it's y. G is a constant. It's always 9.8 meters per second squared. And then the t would be given to you, the time that that object is falling. And then you would just square it. Okay? The next equation is about how far an object would travel horizontally. So we call that x, like the x-axis going horizontally. So you would just take the speed times the time. So you would be given 2 out of the 3 of these. I would give you velocity and time, and then you could calculate how far. Okay, so if you knew that it was traveling at 10 meters per second and it traveled for 2 seconds, then it would be 20 meters would be how far that object would travel. You would multiply them. And the final one here is if you launched a projectile at an angle, you would use this equation to find out how far it would travel. This puts it all together. It puts the vertical and horizontal components together. So you would take the first speed that it was, say, shot out of the cannon, maybe that was that 20 meters per second, times t, maybe it's traveling for 5 seconds, times 0.5 times 9.8 times your time again squared. All right, that's a lot. I probably will not give you a problem like this on the test, but I might give you one of the other 2. And that should complete our notes. All right. And I'm going to come back here. Oh, wow, 1 minute to spare. Okay, so next week, we are only going to be reviewing. We're going to have a study guide, which won't be due for a grade. We will review the study guide. We'll get you prepared for the test. And I'm also going to share with you like a slideshow of, we'll do our year in review. I have some pictures of us throughout the year that we'll share. So next week's just a review. Note, this is the last of the new material. Test is a week from tomorrow. Study guide will come out on Sunday, not due for a grade. Don't forget Angry Birds, and these notes are due tomorrow by 2 p.m. All right. If you need anything, I can't stay after class right now because I have another one, but you can come see me in my office hours today at 2 o'clock, or you can message me on EdSpeak. And I hope you guys all have a great day. We only have one more week and a week and a day left, guys. We got this. All right. I'll see you.